Good morning, everybody. Today I would like to show you my work. I won't read the title again. The aim of the work was the investigation of the fracture behavior of acrylic resins and their relevant composites, with particular focus on the effects of viscoelasticity on such behavior. These are the key topics that will be covered during this presentation. And starting with the materials, we studied two thermoplastic acrylic resins developed by Arkema company. One plain and one rubber toughened, named Helium and Helium Impact respectively, which have similar glass transition temperatures. Also, we found for the toughened material transition for the rubbery phase at around -25 degrees. The same two resins were adopted to prepare by infusion molding unidirectional carbon fiber composites with a final fiber content of around 65% in weight. So the fracture was investigated for the matrices with the double torsion testing configuration, which shows this configuration, apart for its experimental simplicity, also for the possibility of having a stable crack growth, and the fact that the compliance of the specimen is linear with the crack length. Therefore, it's the derivative of the compliance with respect to the crack length, the term dc over dA, is not dependent on the crack length, but and is constant for given test conditions. This factor and the fact that the load remains constant for a certain phase of the test, as we can see from the typical load displacement curve of double torsion test. So we have that both the fracture toughness and the crack propagation speed are constant, making their correlation very easy. Actually, the results obtained were corrected for the larger displacement. And here we can see the results of the test performed at 23 degrees at the different constant displacement rates. And in order to extend the experimental window, we performed the tests at different temperatures, and then applying the time temperature superposition principle, we obtained these master curves at the reference temperature of 23 degrees. And we can see that the two materials exhibited a different behavior. In one case, we had an increasing trend of fracture toughness with the crack propagation speed, as expected by Viscoelastic fracture theories, while in the case of the toughened resin, we had a decreasing trend. So now let's see some Viscoelastic fracture theories, and we adopted the one proposed by Williams, which is based on the assumption that the crack opening displacement is constant, and that both relaxation modulus and yield stress can be expressed as power laws of the time and time to yield respectively. So if we express the fracture toughness as the product of the crack opening displacement and the yield stress evaluated as at a certain time T alpha, where T alpha is the time necessary to a crack that moves at constant speed A dot to go through the length alpha, which is the length of the process zone. And adopting the Dugdale model for the length of the process zone, we can combine all this expression into the expression of the fracture toughness, obtaining this relationship between G1C and the crack propagation speed, which is a power law as well, with an exponent which is related to the exponents of the power laws of the relaxation modulus and the stress. So now we needed these exponents, so we performed dynamic mechanical analysis in a 3-point bending configuration with these parameters of temperature and frequency, from which we obtained these curves for the relaxation modulus. And we evaluated the values of the exponents for the two materials. The yield behavior was investigated in uniaxial tensile tests performed at different displacement rates and different temperatures. Then we plotted the yield stress as a function of the time to yield, and we did again the master curves at the reference temperature of 23 degrees, from which we obtained these values for the exponents. So now, with these values of m and n, we were able to evaluate the theoretical value of the exponent of the G1C A dot relationship. And we can see that there is a fair agreement between the theoretical and the experimental value obtained from this data. In the case of the helium raising, the plane raising, while as already said, we can see that in this case we have a decreasing trend, so there is no agreement with the theory, and we thought that this was maybe due to a change in the damage mechanism occurring inside the material. And we know that in a homogeneous polymer we can have crazing or shear yielding, while in the case of a toughened polymer we can have multiple crazing, which is obviously related to crazing, but with high number of crazes, which involve higher levels of energy absorbed. We can have cavitation of the rubber particles, and we can have shear yielding. Actually, these two are related, since the cavitation of the particles promotes the shear yielding of the surrounding matrix. And since these different mechanisms are related to different changes in volume, it is possible to study this mechanism, and actually it was done in several works present in literature, to investigate this mechanism by studying the volumetric strain. And we can see that when the main mechanism changes from multiple crazing towards cavitation and shear yielding, we have a decrease of the slope of these volumetric versus linear strain curves. And this can be due, as in the case of the first plot, to different material properties, or for the same material, for example, for different strain rates. So we studied the volumetric strain by performing tensile tests where the deformations were evaluated with digital image correlation, and under the assumption of transversal isotropy, we measured the volumetric strain with this relation. So here we can see the results of the change in volume versus the linear strain at a given displacement rate and at different temperature. And in the second graph, we can see that the results for a given temperature and at different displacement rates. So, summarizing the results, we can say that for increasing rates, we have that the main mechanism moves from cavitation and shear yielding towards multiple crazing, while at higher temperatures there is more predominance of cavitation and shear yielding. With that in mind, and knowing that cavitation and shear yielding are related to higher levels of energy dissipated, we may explain the trend we found from the double torsion tests. For what concerns the composite materials, we investigated the fracture with the double cantilever beam testing configuration, from which, knowing the load, the displacement, and the crack length, we were able to measure the fracture toughness with the correct ability, which shows the value of fracture toughness as the steady state value of the curve, where the crack propagation speed was measured directly from the video recordings. So we adopted the same procedure as for the matrices, and we performed the tests at the different rates and at different temperatures, building the master curves at the reference temperature of 23 degrees. And here we can see these curves along with those of the relevant matrices. And we can say that the dependence of fracture toughness on crack propagation speed is transferred from the matrix into the composite, and that the presence of the fibre gave an enhancement of fracture toughness, meaning that there was no physical constraint on the development of the process zone, for example, and that we can see that the effect of the presence of the fibre is slightly more pronounced at lower crack speeds or higher temperatures. So, concluding, we've seen that in the case of the plane racing, the helium racing, there was a good agreement between the experimental results and the viscoelastic fracture theory. While in the case of the toughened racing, there was a change in the damage mechanisms at the different test conditions, which gave the inverse trend. And also we've seen that the fracture toughness dependence on the crack propagation speed was fully transferred into the composite. And we are now currently working on better understanding these toughening mechanisms in order to confirm the indications obtained from the volumetric strain studies we've seen. And I would like to thank the Italian Association of Macromolecules, Associazione Italiana di Scienze e Tecnologie delle Macromolecole, for sponsoring my presence here at ECF 21. And also I would like to thank you for your attention. And